by other enzymes. If you want to detect a signal for the energy state of the cell, and you want to do that effectively, then why would you look at ATP if ATP is being maintained high and constant, right? I mean, it's high, and we just used up a lot of it. Let's say 0.5 millimolar is a lot to use up, but we still have it pretty high, and it's not that different. It's only 10% off. Right? On the other hand, AMP just shot up 600%. So there's an enzyme called AMP-activated protein kinase. This is the only time we'll look at it. It's not in one of our pathways. But it's a metabolic enzyme that's in all these different tissue types in the body. It's a kinase, so it phosphorylates stuff. And if the AMP levels are low, and it's responding to the AMP levels. So if the AMP levels are high, it's active. If the AMP levels are low, it's inactive. If it's active, it's phosphorylating stuff. And the stuff it's phosphorylating are enzymes. And the enzymes that are regulated by phosphorylation. And so, for example, in the heart, those enzymes would be the ones that oxidize fatty acids. Why? Because we're going to get energy out of that, and it's AMP. So the energy starts, so we've got a signal that it was low. So any place that this thing is active, it's going to be doing stuff that helps you get more energy. Fatty acid uptake, oxidation, glucose uptake, etc. Here, it's going to be doing things to turn them off, like making more fatty acids. Not a good idea if your AMP is low. Sorry, if your AMP is high, I mean, because it signals that your ATP must be low. So that's an important enzyme. If you go on to take medical biochemistry in professional school for whatever reason, I have a feeling you'll interact with NMPK a lot more. Okay, so we'll come back to that other point on the flux regulation. It's not really that important of a point. But I just want to highlight, why must ATP be high? There's two reasons. Well, it has to be high because it has to drive the cell and provide the energy currency for the cell. So we can talk about it kind of like that. But we could say, well, what happens if it's not high? Right? So there'll be thermodynamic effects because there's all these reactions that go ATP to ADP, for example, and back again. So the relative amount of ATP over ADP, for example, right, that ratio is clearly critical to determining Q. Right. So we call these thermodynamic effects because we're talking about Q, which is like K. Right? So it's a thermodynamic parameter. It's a driving force to get you a delta G. Right? It's not really about how fast. It's more about a thermodynamic parameter. Right? But the other thing is that there's a kinetic effect. Right? And the kinetic effect has to do with where you are on the V versus S curve. Right? So if ATP is, S is ATP, let's say, and it's depleted, then your velocity also went down. Right? So that's a kinetic. So depending on what the Km is and where you are with respect to it, it could drop a lot or a little. And of course, if this is a sigmoidal curve, it might drop a lot more. So really, it's the sigmoidal curve that's probably more relevant to think about. Right? So there's a delta velocity. Here's a delta S. So it's important to distinguish kinetic effects from thermodynamic effects always, and I try to do that sort of throughout our discussions. But it's particularly important when we're talking about ATP. Everything is more important when we talk about ATP. Questions? Okay, if you did not pick up your midterm, they're over there. And I'll see you all on